Hello, my name is Paul Price, and this presentation is about why methane matters in climate action. And first, some context. Here we are looking at Ireland's per capita greenhouse gas emissions compared to the EU average, and we can see carbon dioxide emissions in black here are above the EU average. 84% of those are from fossil fuels, but there's also some cement emissions, and 12% of these are from land emissions, particularly from soils, organic soils, and from wetlands. When it comes to non-CO2 emissions, Ireland has particularly high non-CO2 emissions of nitrous oxide, that's N2O here in orange, and methane, CH4 here in blue. And these are triple the EU average. Most of these, 93% of each of these, are from agriculture, mainly from fertiliser and cattle emissions from digestion of carbohydrates, which creates methane. In terms of global context, these charts come from the summary for policymakers from the Intergovernmental Panel on Climate Change's SR15 report. That's the report to do with what it would take to meet the Paris Agreement temperature targets. And these charts assume the temperature targets are met by about 2100, so that global warming returns to about 1.5 degrees Celsius, possibly after some overshoot, by about 2100. So all of these charts run from 2010 through to 2100. The large chart is for carbon dioxide, and the charts on the right are for non-CO2 emissions. And what's important to realise is that these charts all correspond to each other. So if we don't reduce methane emissions fast enough, then we have less carbon dioxide budget. Looking at the carbon dioxide chart, you can see that we're at 40 billion tonnes of CO2 emissions per year globally right now, but emissions have to go all the way down to net zero by 2050 and even go net negative after 2050 for a period depending on the pathway followed. And that means achieving negative emissions potentially of CO2, so that's CO2 removals being removals from atmosphere faster than emissions. On the right-hand side, we can see what these very difficult CO2 emissions pathways correspond to, and we're looking at methane emissions globally down by 50% by 2050, and you can see that between 2020 and 2030 particularly, there's a very sudden drop in methane emissions. So that means achieving some serious mitigation globally in terms of all methane emissions, which are both from fossil sources and from agriculture. And there's some emissions from waste as well, but mainly fossil and agriculture. So we also have at the bottom here nitrous oxide emissions, and you can see that the bulk of pathways are looking at about a 20% cut in nitrous oxide emissions by 2050. There are some pathways with more than that, and that's to do with often fertilizer for bioenergy to create enough bioenergy to achieve bioenergy with carbon capture and storage, which isn't viable yet, but that's what that's about, those extra nitrous oxide emissions. So globally, we can look at historic emissions up to 2020, and that's what you see on the left-hand annual emissions chart here, is emissions of carbon dioxide in black are rising very quickly. Nitrous oxide emissions in orange are also rising, and then the dashed blue line shows the flow of methane emissions. And what's also interesting in this chart is that we actually have a solid blue line which comes from this new metric called GWP star, which reflects the warming due to the dashed flow of methane. And so that as soon as you start reducing the flow of methane, you actually get into negative values for warming reduction for a period of time. Now, on the right-hand side, you see the cumulative emissions corresponding to the annual emissions, and these charts all run from 1850 right up to 2150. And what we're seeing after 2020 in the annual emissions chart is a scenario, an imagined scenario, where we cut carbon dioxide, nitrous oxide and methane by 3.5% per year. So each of those gases reduced by that amount. And the cumulative result is on the right-hand side. And by doing this, one just about enables a well below 2 degrees Celsius scenario corresponding to the Paris Agreement. And you can see that by reducing the long-lived gases, carbon dioxide and nitrous oxide, as you reduce them, the amount is still rising until it gets towards zero, then it levels off in total cumulative terms. But what's very interesting is that by reducing the flow of methane emissions, you actually enable the total warming corresponding to the cumulative warming for methane actually reduces. So because it's a short-lived gas, if you reduce the emissions, then there'll be lower concentrations in the atmosphere because the methane decays in the atmosphere, and that means the warming impact actually reduces. So you don't get cooling, but you get a reduction in the amount of warming that's due to methane in the atmosphere. So now looking just at methane itself in terms of pulse versus stable emissions, and when we talk about pulses of emissions, that's one emission really, but we can use that to approximate for annual emissions. So this is annual emissions, if you like, versus stable methane emissions. So here we see a methane pulse emission, which we can take to represent the effect of 1 year of methane emissions. And we see here in the chart the relative impact over time, and you can see the years running along the bottom here. So this assumes an emission that occurs in 2010. And in the blue line, you see that immediately you emit the methane, you get the full amount of its radiative forcing. The climate forcing impact is immediate, and then that reduces exponentially over time. So there's very little of it left in terms of forcing by 2060. But there is some remaining radiative forcing. And then the temperature change, the warming effect, is lagged by about 10 years or so. And that has a maximum warming impact about a decade later. So what we're saying there is that the science on the left-hand side here is that, the maximum warming impact is about a decade later. But what's important to realize is that after this peak, the warming effect reduces, but it still adds to warming, and any future pulses are overlaid over this existing warming. So this tail effect of every emission is very important. So, and when we talk about a methane's lifetime, really this is a half-life, if you like. It's the point at which there is the maximum warming effect of the methane is there. So what we hear on the right-hand side, sometimes we hear this fictional statement that within 10 years methane is destroyed in the atmosphere. Well, this isn't correct. As we see on the left, and we saw in the previous chart, there is still a warming effect. It's just decaying, but it's still very important. So here's an exchange on Twitter with Dr. Frank Mittliner, who was saying that within 10 years that methane is destroyed into the atmosphere. I pointed out that the article that he referenced was saying that the 10 years is a half-life for methane, and he did agree that that was correct, but unfortunately in future presentations this hasn't been made clear, which is a bit of a problem. Now, when it comes to a sustained stable flow of methane emissions, this is really quite different to a single pulse or a single year's emissions. So if you started up a source and the methane was then stopped and there was no more emissions from that source, then that would be like a pulse of emissions. But if you switch on a source of methane, or you have more cattle, for example, then you would have a sustained flow of methane emissions, and that creates a very different effect. And as I was saying, the pulses effectively overlay each other. So on the right-hand side here, you can see each pulse of emissions and the warming due to each pulse, and how they essentially lay over each other to create increasing warming. So this only stabilizes after 20 to 50 years. And you get up to quite a high level of warming that's about 25 to 30 times the level of a single pulse. This is very different from assuming that the methane completely disappears after 10 or 12 years. As you see on the left-hand side, the correct warming level from a stable methane flow is quite high, but if you assumed it all disappeared after 12 years, it would be apparently only a quarter of the actual level. So one should be very careful about not misleading in terms of what the actual effect of warming is in terms of pulse versus stable emissions. And of course, it doesn't matter that methane has a short lifetime, because all of these pulses may have a short lifetime, but they add up to a very large amount of warming compared to a single pulse. And that means that you can have a very big effect from increasing the flow of methane. And similarly, if you reduce the flow of methane, you actually reduce the amount of warming due to a methane source or due to a sector. So I'm going to talk about some greenhouse gas equivalence metrics. There's GWP 100, which is currently used in UNFCCC reporting, and that's the global warming potential due to a greenhouse gas emission after 100 years compared to carbon dioxide. And so it's in units of CO2 equivalent, CO2 EQ. This new metric, global warming potential star, GWP star, is actually the change in total warming level due to an annual SLCP emission. An SLCP is a short-lived climate pollutant, and the biggest and most important one of these is methane, and so that's true globally, and it's also very important, as we've seen in Ireland, and it's measured in terms of CO2 WE, that's warming equivalent CO2. And the interesting thing about this is that for every ton of methane per year flow represents a one-off emission of 2,400 tons of CO2. So if you can reduce the annual flow by 1 ton of methane per year, so if you reduce the flow ongoing annual emissions by that amount, that's the same as removing 2,400 tons of CO2 from the atmosphere. Alternatively, if you increase methane flow, then again you're potentially acting as if you're adding 2,400 tons of CO2 to the atmosphere. So these are very significant warming or warming reduction effects that you can exert by changing the methane flow. So GWP star simply approximates the outcome of climate models. And we saw the build-up of an ongoing flow of methane, and you can see that in blue here how a climate model represents that build-up in terms of total warming equivalent emissions, and then you can see that GWP star echoes that. It's not exact, but it provides a reasonable approximation, especially across a whole system of emissions, to what a climate model shows you. Whereas for this new methane source from about year 0 here, you can see that the GWP 100 metric actually undervalues a change in emissions from methane. So really GWP star does a good job of showing this immediate effect over the first 20 years or so, and then a much smaller effect over the longer term. And that's why GWP star is particularly useful, and it just uses the standard time series of GWP 100 data in order to come up with an answer in terms of the total warming. Now here we see a bathtub analogy, and obviously it's an analogy, so you can critique it in certain ways, but hopefully it's somewhat helpful to see what's going on when you emit some methane. And what you see here is a big tap, which represents the methane flow and ongoing flow, or which you can turn up or down. And you also see a very small tap, which is the methane stock tap. And for every emission of methane, you get a small amount of stock effect, which is very long-term warming. And that's about a quarter of the GWP 100 value. So if you were emitting, say, 4 tons of CO2 equivalent methane, then that's actually 1 ton of CO2 equivalent very long-term warming in this stock effect. And that's to do with actually the oceans warming up over about 300 years. But what we can affect is the methane flow, and if you turn that down, then that can offset the stock effect and more, and actually we can result in warming reduction from turning down the flow. And similarly, if we turn up the flow, well, that boosts methane warming considerably and raises the level in this bathtub analogy, which results in warming and results in a higher GWP star, which in CO2 equivalent, which is equivalent to the warming. On the left-hand side, we see the formulas, but although it's presented in one way in the paper, in Lynch et al., the most recent paper from the Oxford group, the second equation here is very useful because it separates these flow and stock terms. So here we see a new methane source starting from year 0. And in this example, we've got 1 new kiloton of methane. So a new source starts up with 1 kiloton of methane per year being emitted. And here we are assuming that the GWP 100 value for methane is 32, which is what's used in the Oxford paper, Lynch et al., the most recent Oxford paper. Whereas in the UNFCCC, there is a GWP 100 of 25 currently, although that's shortly going to be changing to 28. But here we're using 32. And so we have this all on the same chart. We have annual and cumulative emissions. And down in brown here, you can see that we only have 32. We have a result is 1 times 32. So that's 32 kilotons of CO2 equivalent per year. But the result of this ongoing annual flow is initially we get an annual GWP star value of 128 for the first 20 years. And this results in getting to a cumulative GWP star flow of 2,400 kilotons of CO2 warming equivalent in the mauve line, which is going high up here. We're also getting a much smaller ongoing stock flow of 1/4 of the annual GWP 100 value of 8 kilotons per year, and that adds up to 160 kilotons of CO2 warming equivalent. And so that's why in total we get this blue line after 20 years of 2,560 kilotons of warming equivalent. And after we get to that 20 years and using GWP star, we only get this small stock component rise, and the flow levels out at this level. So that's the stable flow equivalent level, is 2,400 kilotons of CO2 warming equivalent. But that comes from just 1 kiloton of methane per year source. So the result is we get 2,400 kilotons of CO2. That's the one-off addition to the atmosphere of CO2 that will be equivalent to this flow. And so this is quite a huge effect of a change in methane flow. And similarly, if we then cut this source or reduced it, then we will get a similarly large effect. One thing that is out in the literature is that somehow a large cattle herd is like a closed fossil fuel power station. And this is quite a misleading thing to say. And so this is why this isn't true. Here we have the new source beginning, as we saw in the previous chart, and we get a new source emitting methane. And initially we get a very big rise in its warming effect. And that after 20 years still rises from this stable flow, but rises much more slowly. And in this example, we're going to stop the methane source after another 20 years or so. By comparison, we can see that a carbon dioxide source with the same equivalent CO2 emissions goes up at the rate we see here in the orange line, and then it stops emitting. And of course CO2 stays in the atmosphere, and so we've reached that height, and that's the rate we're going to stay for a closed power station. Whereas if we have a very large cattle herd, we can actually reduce the numbers and the inputs of feedstuffs going into digestion of the cattle herd, and if we do that, then we can cut the total warming effect by a very considerable amount. And in terms of societal cost for climate action, that might be a far faster, easier, less costly way of doing climate action than removing CO2 from the atmosphere. So as a way to achieve sort of negative emissions, but the equivalent effect as removing CO2 from the atmosphere, if we have a big source like a large cattle herd, then it might be a lot cheaper to actually reduce those numbers and inputs. So looking at the Irish case particularly, then what's really important is that ongoing annual methane emissions do sustain a warming equivalent. As we've said, even 1 tonne of methane per year flow is the equivalent to a one-off emission of 2,400 tonnes of CO2. That doesn't mean every year we're adding another 2,400 tonnes. It just means if we keep the flow at that rate, that's what is the equivalent amount of CO2 that we've added to the atmosphere. But this is what we should acknowledge, that if we have an ongoing flow, then like even a constant cattle herd with the same inputs per year, that actually equates to a large amount of greenhouse gas emissions or CO2 equivalent emissions that could be reduced by mitigating the flow. By cutting the flow of methane, you're going to get a large warming reduction. And if we look at the warming level in CO2 WE corresponding to the current emissions rate, we see here from 1990 to 2015, we see for a national total in black, we've got agriculture in purple, waste in blue, and energy in yellow. And you can see that most of the methane is coming from agriculture. But that did increase till about 1997, then it reduced until about 2011. And then due to policy change to push for expansion of agriculture, particularly in dairy, we've had this increase in methane emissions in recent years. So we've gone from going down every year in methane total impact, and then it's going up again. But what's really noticeable is the amount of CO2 that this represents in warming terms. It's over 1,200,000 kilotons of CO2 warming equivalent that's being sustained by the current level of dairy and beef production in particular through ruminant emissions. And maybe that's part of in fair share terms, one thing that Ireland could be doing is reducing methane, as well as reducing CO2 and nitrous oxide. And here we have a chart of GWP star implications for Ireland. And as we said, each tonne of methane annual emissions does have a long-term warming equivalent impact of about 8 tonnes of CO2 to the atmosphere. And that's a quarter of the GWP 100 value of 32 that we've been using. And as we've said, this very large mitigation impact if methane flow is reduced. Here we have some figures, and the 2005 is the EU base year for methane emissions, and you can see that in 2005 that a sustained flow at the 2005 level emissions is the equivalent in cumulative warming terms of 1,305 million tonnes of CO2 added to the atmosphere. And that's a huge amount when you consider carbon dioxide emissions from fossil fuels are about 38 million tonnes of CO2 per year currently. Then you can see that this amount, if you could reduce that amount, that would be a significant contribution to climate action. And that was the case, as we saw until 2011. Things were going down in terms of emissions. They'd fallen by this 149 million tonnes of CO2 WE for the stable flow, but now they've gone up again, and by 2018 we're above the 2005 level. Obviously the stock level is quite small, but what's really important is the flow amount, and you've really got to be reducing methane every year for climate action. And agricultural methane I've put separately here, so that in 2018, the flow is equivalent to 1,245 million tonnes of CO2 WE. Here we have a comparison of two scenarios. One is a scenario where we continued mitigating methane from 2011 on through 2020 at the same rate as had been occurring, and so that would, in a pro rata terms, easily have met the 20% reduction compared to 2005 by 2020. But that's not what happened, of course. We see actual emissions rose to 2020. And in these two scenarios, we simply level off whatever the emissions are in 2020 from then onward. And in the left-hand side, in annual emissions terms, you can see in GWP 100, we've got the actual and mitigation pathways. But then below that, we have the GWP star pathways for exactly the same scenarios. Actual in orange, mitigation in blue. And we see that from 2011, the actual emissions pathway diverges from the mitigation pathway by an even larger amount than the GWP 100 value. So actually using GWP star magnifies the difference between these two scenarios. And you can see on the right hand side the cumulative warming effect of these starting from 0 in 2005 as a reference, but we've got to note that 2005 0 in the chart actually equates to the total warming level being sustained by methane at the 2005 level of 1,245 million tonnes of CO2 WE. So we can't ignore that level of warming. So these charts are just to show the difference between these two scenarios over time. What we see then for GWP 100 is that we have rising methane emissions because of the way this metric works. We just always, in cumulative terms, GWP 100 is always positive, so it's always going to go up. As long as there's some methane emissions, it'll go up. And we can see the difference in the two pathways is 100 million tonnes by 2040 in our two scenarios. But we see in GWP star terms a very different outcome. In the actual case, we end up with emissions rising very considerably, and we know we've stabilized at 2020, but the actual outcome has a 20-year lag. As we know with GWP star, it has this lag time for the full effect of the last change in emissions, which is like in 2020. So there in this scenario, and we see that the outcome is that we actually rise emissions by about 270 million tonnes of CO2 WE relative to 2005. Whereas if we had stayed on the pathway, we would have ended up with a reduction of about 120 million tonnes. And the difference between these pathways is 400 million tonnes. That's 4 times the amount of using GWP 100. And so GWP star really does starkly show the difference in these two scenarios. Here we see some modelling from our recent DCU project, for which the report is just coming out now in late 2020. And these are Irish scenarios trying to hit a well below 2 degrees C fair share target by 2100. And in the cumulative charts, that's the lower charts in these two scenarios, you see a dotted level red line, and that is the fair share below which the solid red line in those lower two charts has to get to by 2100 or before in order to comply with the Paris Agreement target of well below 2 degrees Celsius. And the report details how that's defined. But for these purposes, what we're seeing here is how we would meet the Paris Agreement with different mixes of greenhouse gas pathways. On the left-hand side, we have, in the top left-hand side, we have the flat scenario here, where we have carbon dioxide emissions going down quite quickly, slowly at first, and then much more quickly and through net zero by 2050. That's the black line. Black lines are carbon dioxide. And then in the flat scenario on the left hand here, we have, as you can see in annual emission terms, for the dashed blue line and the solid orange line, that's methane and nitrous oxide flow, they are flat right to the end of the century. But as you can see here in the lower chart, cumulative from 2015-2100, in the flat scenario, the red line, the solid red line, is massively overshooting the dotted line. And therefore you need large amounts of CO2 removals from atmosphere, negative emissions, in order to get the solid red line back to the Paris level by 2100. And that's what you're seeing in the annual chart above. You see the black line going through net zero and then going very negative to the point of being about 36 million tonnes of CO2 removal every year. And so that's like the current emissions of CO2, except we're actually growing enough wood or capturing enough CO2 from the atmosphere and putting it in a very safe place, probably in geological reservoirs via carbon capture and storage, very expensive to achieve, and you'd need an infrastructure equal to today's fossil fuel industry just to put that underground, as well as getting the whatever energy you can get while doing all this. So that makes it seems like it's very, very difficult to keep methane and nitrous oxide at the current level. It's probably impossible and requires massive amounts of storage of carbon dioxide removals. On the right-hand side, we have a scenario where we reduce methane and nitrous oxide by 50% and then go flat. And then that means that you have much lower requirement for negative emissions, the annual emissions of CO2 below zero, but by reducing methane you get actually a negative emissions outcome effectively in terms of warming terms, a warming reduction, which you can see in the cumulative chart below on the right hand side, and that enables you, the red line, the solid red line, to actually get below the Paris level by before 2060 and with minimal overshoot and duration of overshoot. So by cutting methane and nitrous oxide by 50% by 2050, this goes a long way. In addition to having to do the CO2 reduction, this enables one to hit a Paris target much earlier. But you do have to do it, so that means doing everything. On CO2, really massive change, but on nitrous oxide and methane, it does mean cutting those by 50% by 2050. So we've compared metrics, and here I'll just put these up to show that the difference between GWP 100 and GWP star. So GWP 100 isn't a great metric for methane mitigation, and it fails to show the really strong effect of changes in flow, but it's still very useful in showing the actual level of flow, and therefore that's what we're actually controlling by policy. So we need to be targeting reduced emissions, reduced annual flow of methane over time, and so at least GWP 100 is showing that. Whereas GWP star really does accurately approximate methane warming and particularly any changes in warming, and that enables methane to be included in cumulative carbon budgets from a particular base year and relative to a particular target. And so not only is it useful for approximating warming and warming changes, but it actually it doesn't have to be just separating methane. It actually enables inclusion of methane with nitrous oxide and carbon dioxide in meeting overall carbon budgets. And what we must note, of course, is that GWP star doesn't change climate science. Methane's behavior in terms of warming and warming reduction is well understood. So it doesn't change the climate science. It does enable inclusion of methane with CO2 and nitrous oxide in carbon budgets. And it's important to note that GWP star has already been discussed by the IPCC in SR15 Chapter 1. It's very important to note that in any adoption of GWP star really involves some serious equity issues, particularly if you're just using it in the way the Oxford Group has proposed it relative to 20 years ago. This is all sorts of equity problems which would need to be considered in terms of things like the Paris Agreement. Now I'm just going to go through some methane clarifications, considering some of the confusions that are out there currently. And this is kind of a list of clarifications that I make in the following slides, and we'll go through them one by one. I've got them in bold and then in non-bold text here, but that's just to differentiate the different ones. But we'll go through them one by one. So one thing is that claims regarding methane can mislead by error or omission. And here's a claim that if a country like Ireland, New Zealand or the United States keeps their livestock herds steady, then they keep their methane steady. Well, this can be false, because if you have constant methane emissions, as we've seen, the warming effect still rises at a slow pace, but nonetheless it does rise at a quarter of the GWP 100 value per year. So if, as in Ireland, we have 16 million tonnes of CO2 equivalent emissions in methane, in total methane, then a quarter of that, 4 million tonnes, is a long-term stock effect. So even 4 million tonnes, that's quite a lot in terms of our overall contribution to global warming. So even keeping livestock herd steady, if that's the outcome, millions of tonnes just in the stock effect, then that is a significant methane emissions that needs to be reduced. It's also a problem that carbohydrate intake per head for cattle has steadily increased, particularly for dairy cattle in Ireland, but also in the USA, for example, because you have greater fertilizer on grass and more feed inputs, or you might have less feed inputs, but overall the overall inputs have gone up, and therefore even with a stable herd, you're going to get more methane because you have higher inputs. Another thing that's omitted in this kind of discussion is that the fact is that in Ireland, both cattle numbers and dairy inputs per head have gone up. So the result of having this more efficient, i.e. profitable production, is you get cost savings and you have no limit on the amount of nitrogen, so there's no milk quota. So that enables you to have more cattle and inputs if you make sense, financial sense to, and the result is more methane because there's no actual control on methane. There's no penalty or not enough of a penalty or any restriction like the milk quota. So if you're going to make these kind of claims, you can mislead by omitting this kind of information. And we have a similar claim below, and it's a similar one, but one thing that's omitted is that it's not just about changing or an increased or not increasing global warming. What's omitted is that the ongoing methane emissions of a large cattle herd at the national level means that is sustaining a very substantial amount of methane warming, and if you reduced the cattle numbers and inputs, then that would reduce the level of warming. A very important point is that choices do matter, and that agriculture's biogenic methane is anthropogenic. And it's a bit unfortunate that we see the recent Climate Change Advisory Council report emphasising biogenic as if that's somehow of more importance than the fact that animal agriculture's biogenic CH4 is anthropogenic. And that means we can control this. We know this because we, through policy, by having a milk quota and so forth, then and some constraints on beef farming, then we had reducing emissions up until 2011, when there was a policy decision to target the end of the milk quota, and that's what's led to more cattle and more use of nitrogen, resulting in more methane. And so we can see how human policy choices matter. And we have had a very large effect by that basically targeting policy that's against climate action by allowing more methane from this biogenic but really anthropogenic source. A very important point is that cutting all methane emissions fast is more important than the fossil versus biogenic difference. And you can see this very clearly from these two tables. I say very clearly, but you've actually got to go and read the tables and the notes with the table, so perhaps it's not that clear really. But really, fossil methane only has a very small amount of additional warming in addition to biogenic. And if you want to account for that, then the GWP 100 values would actually increase for fossil very slightly, but the numbers are given for biogenic methane. And so really there isn't much difference between biogenic and fossil. What's more important is that we need to cut methane emissions from all sources, whether they're fossil, agriculture or waste. We need them to be going down, and the total needs to be going down every year, and that should be the policy target. So here's the second table which I'm pointing to, and again it's really pointing out that there's not much difference between fossil and biogenic methane. So the important thing is really about whether to emit methane or not, and we can make that decision. Another misleading thing is we get this argument that there were somehow more cattle in the past, or more buffalo or so forth, but this simply isn't true. It's not true in numbers, and it's also of course not true in the fact that we've got much higher inputs overall. We're using a great deal of nitrogen on cattle feed and on grass, which is going to cattle, which is digested mostly by cattle. There's also sheep ruminants too, but mostly by cattle, and that's resulting in increasing methane emissions. So it's simply not true. This kind of bogus argument is just not the case. As we've noted, then what matters is that ongoing emissions result in a high level of warming. And this is true for, as we see here for Ireland, this is for 1850 up to the current day, using data that's available. And we can see CO2 emissions in black here rising from 1920 or so for Ireland and going up to this level of about 2,200 million tonnes of CO2 WE. But this only exceeded the total from warming from methane just before 2000, as you see where the black line crosses the blue line. And notably, we can see the livestock methane level in brown here is a very significant amount of warming. And of course, we've got a lot of animal nitrous oxide from fertilizer that's going on to grass, which is also mostly relevant to livestock. And so those have a significant total warming impact. And you can see that there's been a bit of a reduction recently in methane warming, but not hugely. It's only about less than 5% you would say in total warming from livestock. But as we know, that lag effect continues, but then that's going up again from 2010 onwards. So we've got a very significant amount of methane warming that could be reduced if we reduce methane, whereas the CO2 warming will only go up. What we have to do is level off the total warming by reducing CO2 to net zero as soon as we possibly can by using less fossil fuels, but by cutting cattle numbers and inputs, really by cutting the total amount of milk production and beef production, also sheep too to a lesser extent, then we can cut this total methane warming, and that would help to reduce the total warming. And while we're doing that, then because nitrogen inputs really are what to a large extent are driving this production by putting nitrogen fertilizer on grass and also importing nitrogen in feeds, that will also, by cutting nitrogen, it will cut both the nitrous oxide emissions, and so we can level that off, but also it would cut the overall warming from methane. One thing we heard recently, and that there's been this discussion over what's the overall global figure for the impact of livestock on total global warming, and we had this discussion recently where it was put at about 18% or so, and then has been reduced 14.5%, and that makes some sense in terms of the way in which that calculation was done. But it doesn't make so much sense in terms of climate science. And so here you have climate science, which actually says that livestock emissions are about 23% of total warming in 2010. Obviously that changes over time, but we've seen livestock emissions continuing to grow over time, and the more nitrogen being used as well. So even though CO2 emissions have been going up as well, it may be of the same order. So one should be careful about how exactly one is discussing these impacts of livestock, for example. The final point I'd make is that what really matters in climate action is cutting absolute emissions. And all too frequently, even now, after the science has been saying what's required forever, we have these sectoral specific calculations and so forth that are always talking about the carbon footprint or emissions footprint, whereas actually what they're talking about is that not the footprint of the entire sector, but only of one unit of production. And so obviously if you save some money and then that enables you to buy or make more units, maybe you'll cancel out the efficiency. You can say the efficiency has increased, so your emissions footprint has gone down, but overall your absolute emissions might have gone up. And that indeed is what's happened since 2010 in Ireland with agricultural emissions. There's lots of claims that the emissions footprint has gone down, say for milk, But of course, the amount of milk being produced has gone up greatly, and so the absolute emissions for dairy have gone up by, in methane terms, exactly the same rate as the rise in milk production. So policy really does have to cut total inputs and pollution, and you can have direct ways of doing this by directly limiting the total nitrogen inputs to going onto grass or feed for animals. Or we can have an indirect limit by limiting production, as the milk quota did, which acted as an indirect limit on nitrogen inputs, and therefore reduced the amount of methane as farming got more efficient. So measures must add up to action that actually cuts total emissions. So in conclusion, cutting all methane emissions is important. Whether they're fossil or biogenic, what matters is that we can make choices to cut them. I think we've gone through all of these things, that improved efficiency only achieves climate action if total emissions go down. Animal agriculture is anthropogenic for methane, and so we can make choices. And biogenic methane has only very slightly less warming impact than fossil methane. A very important thing is that GWP Star actually enables the inclusion of methane. So we hear a lot of discussion right now from the Climate Change Advisory Council, and even in the current climate bill, that this GWP Star really requires you to separate methane from the other gases, whereas in fact what GWP Star enables is you separate it and you can get a separate CO2 warming equivalent for the ongoing flow of methane, but you can then include it in terms of your carbon budgets looking forward, and so it can aggregate with all greenhouse gases. And not forgetting, the very large warming impact of an ongoing methane flow cannot be ignored. You cannot just look at changes in the total flow relative to a certain date. What's really important is what's the ongoing flow and how much could we reduce it, as well as doing reductions in fossil fuel use. So we need to look at all greenhouse gases. We need to reduce all greenhouse gases as a matter of great urgency if we are to be good faith actors in meeting the Paris Agreement. Thanks for listening.